Let's call this capacitive actuation with AC voltages. And just to kind of recap things, so when we were talking about both parallel plate and comb drive capacitive actuation, we had assumed that all of our actuation voltages or our bias voltages were DC quantities. So in both of those instances, we had used the relationship that our electrostatic force was simply going to be the derivative of the energy stored by the capacitor as a function of displacement. And our energy stored by our capacitor was going to be 1/2 times the derivative of the capacitance with respect to time times our bias voltage squared. Well, as I had mentioned in our last class meeting before I got sidetracked, confused, whatever you want to call it, if our bias voltage is of the form to where we have some DC voltage plus some AC voltage, which I'm going to represent as V naught cosine omega t, then from this, we could express our force as 1/2 times the derivative of our capacitance with respect to position times this big beefy thing right here. VDC squared plus 1/2 V naught squared plus twice VDC V naught cosine omega t plus 1/2 V naught squared cosine twice omega t. All right, so we're going to look at some different cases, but I just want to kind of talk about things really quickly before we get into what those different cases might represent. So as I mentioned in our last class meeting, we essentially have a couple of DC terms here. So these two DC terms are going to be what are establishing what is going to be our equilibrium operating point for our system. So this is just a constant force, or another way to think about it would be a constant force applied to our thing will generate a constant displacement because of our spring constant. That's just setting what the DC operating point of our mechanical system will be. And then we have two different AC components here, and we're going to kind of talk about how they can be used specifically. One is oscillating, or excuse me, one portion of the force is being generated at the electrical excitation frequency. So that's the omega term. And then we have another term, that 1/2 V naught squared cosine twice omega t. And so that force is being generated at twice of our electrical excitation frequency. All right, so let's talk now about time harmonic actuation with a DC bias. So this is kind of a subsection of this. So when our DC portion of our bias signal is much greater than the magnitude of our AC portion, or the twice omega term is much, much greater than omega naught, where I'm just going to make a note here. This omega naught is the mechanical resonant frequency of the system, then our force equation is going to simplify slightly. So our force equation, we'll have 1/2 times the derivative of our capacitance with respect to time times VDC squared plus 1/2 V naught squared plus twice VDC V naught cosine of omega t. So essentially, that very, very high frequency AC term will be very small if our DC bias voltage is much larger than the AC magnitude of the AC portion. And so essentially we're just going to throw that bit away for right now and kind of look at what happens. So I'm going to break this thing up into two different portions. So I'm going to have 1/2 times the derivative of the capacitance with respect to position times VDC squared plus 1/2 V naught squared. And then I'm also going to have, and my factor of 2 out in front of that last term is going to cancel out that 1/2. And so that's going to leave me with VDC times the derivative of capacitance with respect to position times V naught cosine omega t. And so what I have is some DC force here, which once again is just setting the mechanical equilibrium operating point of our system. And then I have some AC force that's generated over here. So this is going to be a time varying, and in our case, because we have simple sinusoidal excitation, it'll also be sinusoidally oscillating force. Okay. So we can rewrite this AC force in terms of what's known as the electromechanical transduction factor. So if we take our force FAC as VDC times the derivative of capacitance with respect to displacement times V naught cosine, sorry, that shouldn't be an omega naught, that should just be omega. We could rewrite this as eta V naught cosine omega t, where eta is simply VDC times the derivative of our capacitance. And this is known as the electromechanical transduction factor. Sorry, I wrote faction, that should be factor. Which essentially relates the generated AC force to the applied AC voltage. So for a parallel plate capacitor, by the way, please tell me if I need to slow down. Yep, all right, let me scroll up a smidge and I'm gonna let you guys catch up. I feel like I'm gonna burn through 4 pages of notes in 20 minutes and then neither of us are gonna have anything to do and we're all gonna be exhausted. So. I spent a large part of my weekend helping my wife take care of my mother-in-law. She went in for a rotator cuff repair surgery, and actually found out that she had two tears in her rotator cuff and also had to have a bone graft. So she effectively had three times as much surgery as she was expecting. And then my wife got sick, so I spent a ridiculous amount of time hanging out with the in-laws, which isn't a bad thing. I love my in-laws, they're great. But my father-in-law loves to put me to work. So I installed a new television in their bedroom since my mother-in-law has to stay just in a recliner so that she can easily get up and go use the restroom. I installed new light fixtures in the ceiling of their pantry. I fixed my father-in-law's computer that I bought him last year because he does not understand how the internet works and just loves to get scammed over dumb shit. And then I made them multiple meals. So that was how I spent my weekend. Are you guys caught up? Okay. All right. So talking about electromechanical transduction factor. So for a parallel plate, capacitive actuator, where I'm just going to make a note here. This is from our notes last week. That would have been, I think, Wednesday. But for a parallel plate device, our capacitance is epsilon A over D minus X, where that X is the position of the movable plate from its unbiased position. So for a parallel plate capacitor, whose capacitance is that? The electromechanical transduction factor is given by following expression. So this is going to be eta sub P, where the P is just for parallel plate. And we're just going to have simply our DC bias voltage multiplied by epsilon A over D minus, and I'm going to put this as XEQ quantity squared. And you may sometimes see this written as VDC times CEQ over D minus XEQ, where CEQ is equal to epsilon A over D minus XEQ. And I'm just going to make a note here really quickly. XEQ is the equilibrium displacement at the DC operating point of the system. What I mean by that very specifically is we have, if we scroll up here, this FDC term that is going to cause some amount of displacement at that particular point where we don't have any AC signal acting on anything. We just have the DC part. That is what I'm considering XEQ. And then CEQ is then the capacitance at that DC operating point. So that is different than the C naught that we talked about earlier. C naught is the capacitance when we don't have any bias on it whatsoever. CEQ is when we have some fixed bias voltage and then we're perturbing it from that point with an AC signal. So I know that there's a lot of different things going on there. I hope I've clarified that enough for everybody. If you have any questions, I would be happy to answer or try to re-clarify that statement. Everybody okay-ish? All right. So let's look at an example. Let's say that we have a parallel plate variable capacitor has an area of A is equal to 100 microns squared. A nominal gap of D is equal to 2 microns, and a DC bias voltage of VDC is equal to 50 volts. If the spring constant of the suspension is K is equal to 400 newtons per meter, I want us to determine the device's electromechanical transduction factor. So the first thing that I'm going to do, even though it isn't explicitly asked of us, and this is just kind of a sanity check thing, is I'm going to try to calculate the pull-in voltage because I want to make sure that that DC voltage isn't super close to the pull-in voltage, because then we're going to have other things that we might have to worry about, right? We could possibly see that our small AC perturbation might push our device into the pull-in range, which would mean that it would no longer work properly. So just as a kind of a sanity check, let's start there, okay? So just as a reminder slash refresher, because we haven't used this in a couple of days, our pull-in voltage is given by the expression 2D over 3 times the square root of twice K sub M, where that's my mechanical spring constant, over 3 C naught, where C naught is the completely unbiased capacitance of our device. Now, we were given our gap distance D, we were given our mechanical spring constant Km, we were not given C naught, so we'll need to take a moment to calculate that to begin with, okay? So, once again, just as a kind of reminder here, for a simple parallel plate capacitor, our nominal capacitance is going to be epsilon A over D, where I'm choosing to use epsilon naught as our permittivity because there has been nothing that tells me that there is not air between my plates. Okay. So that's going to look like 8.854 times 10 to the minus 12 farads per meter. Then we're going to have 100 times 10 to the minus 6 meters quantity squared, all over 2 times 10 to the minus 6 meters for our gap length. And when I threw this into MathCAD, I wound up getting 4.427 times 10 to the minus 14 farads, or 44.271 femtofarads. So if I put this value of capacitance into my pull-in voltage equation, I'm just going to come back up here to the top. I'm going to wind up having 2 times 10 to the minus 6 meters over 3, 2 times 400 newtons per meter over 3 times 4.427 times 10 to the minus 14 farads. And I'm going to square root that thing. And once again, MathCAD gave me a result of 103.482 volts. So just as our sanity check, our DC bias voltage of 50 volts is significantly less than our pull-in voltage. So we shouldn't be worrying about any effects of pull-in in this particular case, right? Okay, so in order for us to determine our electromechanical transduction factor, we need to essentially figure out what XEQ is, okay? So this is going to be fairly similar to what we did in that example problem that I worked when we were talking about pull-in effects. So as part of our derivation of pull-in effects and things like that, there was an expression, or essentially we wound up deriving this expression there, where we could have x cubed minus 2x squared d plus x d squared minus epsilon a times our applied voltage, which in this case is going to be VDC, quantity squared, over twice Km is equal to 0, a third order polynomial, and I'm just going to go ahead and give you the 3 solutions that I found. So my first solution that I found was 7.464 times 10 to the minus 8 meters. X2 was 1.582 times 10 to the minus 6 meters. And lastly, X3 was 2.344 times 10 to the minus 6 meters. So which of those 3 displacements is valid, or is the real one? Number 1. Absolutely right. So it's always going to wind up being the smallest one, just for what it's worth. We can throw this guy out immediately because that displacement is literally larger than the initial gap, which means it's impossible to get. 1.582 microns is well over 1/3 of the gap length. So if we had a displacement of this, our voltage must have exceeded the pull-in voltage, and we did not see that that was the case. That's why I checked it. So the only other one is this guy right here. So our equilibrium displacement from this is then 74.641 nanometers. Using this particular value, then our electromechanical transduction factor NP, which is VDC epsilon A over D minus XEQ quantity squared. Just going to substitute in numbers here. 50 volts, 8.854 times 10 to the minus 12 farads per meters. 100 times 10 to the minus 6 meters quantity squared. 2 times 10 to the minus 6 meters minus 7.464 times 10 to the minus 8 meters. Square that guy on the bottom, and I got 1.194 times 10 to the minus 6 newtons per volt, or 1.2 micronewtons per volt. So essentially, we are going to get 1.2 micronewtons of force for every 1 volt of magnitude of our applied AC voltage that's on top of that DC operating point. Okay. Now, you need to be kind of careful about this result right here, and particularly just because our capacitance and therefore our displacement is going to be nonlinear for a parallel plate capacitor, right? So this electromechanical transduction factor is fairly valid as long as our perturbation voltage is small compared to VDC, right? So if we're talking about 1 to 5 volts or so of AC voltage compared to a 50-volt DC signal, this is probably going to be fine. But if we used a larger AC signal, our analysis might not be as accurate. And it just comes back to that whole thing where we've essentially made an assumption. VDC is much, much greater than the magnitude of our AC voltage, to where we're getting to throw away that 1/2 V naught squared cosine twice omega t term. So just be aware of the potential issues with using these assumptions that we got to this point. If those aren't all valid, this isn't going to give us a pretty accurate model of what's going on. All right, so before we move on to what this might look like for a capacitive comb drive based device, anybody have any questions, or do I need to pause for a moment and let you guys catch up again? North.
If you have 100 micrometers squared, are you also squaring the 100? Or is it like?
So let's go back up here. Yeah, so 100 microns is the length, and then another 100 microns is the height, and I'm squaring both of those things. So I'm intentionally not saying I have 100 microns squared, like where my unit, my area is expressed in microns squared. I have 100 microns quantity squared, so 100 micron by 100 micron plate. So not 10 micron by 10 micron. Okay. Any other questions? All right. So I'm going to put a line under this to let us know this is after our example, just for simplicity's sake. All right, so for a capacitive comb drive actuator, where our capacitance was epsilon NH times L naught plus X all over D. Then that's a total capacitance for N number of finger overlaps. Then we would find that the electromechanical transduction factor is A to C, and that will simply be VDC. Sorry, that should be capital. That's the convention I've been using. Don't know why I switched between them in my notes. Epsilon NH all over D. So as a very quick example for this guy, capacitive cone drive, because it works linearly, is much easier to figure this stuff out. If we have a capacitive cone drive with N equals 100 finger overlaps, a finger height of H is equal to 5 microns, and a gap of D is equal to 2 microns. Has a bias voltage of VDC is equal to 50 volts applied to it. And we want to simply determine the electromechanical transduction factor for this guy. So this will be fairly straightforward because it's just direct application of our expression. So NC is going to be 50 volts, 8.854 times 10 to the minus 12 farads per meter. 100 overlaps. Our height is 5 microns. Our gap is, 2 microns. And this winds up being 1.1 times 10 to the minus 7 newtons per volt, or 0.11 micronewtons per volt for what it's worth. Okay. So capacitive comb drive definitely makes that particular calculation significantly easier. All right. So now let's move on to one of the other cases that I wanted to talk about. So let's say that we have very high frequency actuation. And I'm going to put the boundary on this high frequency actuation up here. So what I mean by high frequency actuation is that the twice omega term of our signal, that twice omega is much, much greater than the mechanical resonant frequency of our system. Okay. So when the AC electrical excitation frequency is much larger than the mechanical resonant frequency of the system, then the generated force, the generated AC force, let me put that specifically, will not cause significant mechanical displacement. So we can kind of think about that in this way. If we try to essentially vibrate a structure, and we try to vibrate it too quickly through our AC excitation, we're not going to be able to induce large displacements, right? So what's happening here is essentially that our AC force under this case is essentially negligible. And the only thing that we are really going to see is the DC force component of our overall force, okay? So this DC force, I'm going to another page here, so I'm trying to make sure you guys have room from this. So from this, all of the generated force will be due to the effective DC voltage, right? So essentially, what we have is our electrostatic force will be essentially all the DC force, which hopefully you recall is going to be 1/2 times the derivative of our capacitance with respect to displacement times VDC squared plus 1/2 V naught squared. Well, we can essentially define an effective VD voltage from this relationship, right? So I'm going to put 1/2 times the derivative of the capacitance with respect to displacement of V effective squared. And then we could define V effective, and I was amused when I was deriving this, and I'll talk about it in a moment. So this is VDC squared plus 1/2 V naught squared, and I just take the square root of this whole thing. So the reason why I was amused by this result, and for those of you that had me for circuits 1 and circuits 2, you'll probably understand this a little. That is literally the exact same expression that we would have developed in those sophomore level circuits classes for finding the effective value of a voltage when we're operating the system, the electrical system, at multiple frequencies, where one of them is DC and the other one is just some AC signal. It is literally the exact same thing. So it's the square root of the square of the effect, sum of the square of the effective values. Way back from circuits 1. So that tickled me. So why is this particularly important? Well, this AC voltage is then contributing to the equilibrium operating point of our transducer, which means that we could effectively accidentally self-actuate a system, right? So what do I mean by that self-actuation? If we had an RF MEMS switch in a high power system, if we applied a large enough AC voltage on top of our DC operating point, we could accidentally cause pull-in effects to occur when we didn't want that switch to be closed. So let's kind of investigate that as a thing just really quickly here. So let's say that a particular MEMS capacitive switch has a pull-in voltage of VP is equal to 7.5 volts. Okay. The DC bias voltage applied to tune the switch is VDC is equal to 5 volts. So essentially we're trying to use this switch type structure as a variable capacitor. We apply this DC voltage, it lowers the overall capacitance, then we're going to put an AC signal on top as maybe part of a filter or something like that. Okay. Assuming that twice omega is much greater than omega naught, what is the maximum AC voltage amplitude that can be applied without causing pull-in. And this is going to be a fairly straightforward process, right? So in this case, what we have is that our effective value is our pull-in voltage. So as long as we're below that, we're good to go, right? So if we know that in general, VP squared could be written as VDC squared plus 1/2 V naught squared, then rearranging this guy, actually I might want to put V effective squared here, then what we could find is that V naught will be the square root of twice the difference, right? So that'll be VP squared minus VDC squared. I believe I've algebraed that correctly. I just moved the VDC squared term over to the left-hand side, multiplied both sides by 2, took the square root of the whole thing. And so this winds up being twice 7.5 volts quantity squared minus 5 volts quantity squared. And then I take the square root of the whole thing, and I wind up getting 7.906 volts. So the amplitude of our AC signal has to be a little less than 8 volts or will accidentally cause pull-in. All right. I'm sorry, what was that? So if our AC signal that is superimposed on top of the DC bias was 7.9 volts or higher, we'll accidentally close the switch. Whether or not we meant to, it's going to close because there's enough electrostatic attraction between the two plates to overcome the restorative mechanical spring force. Sorry, let me get back here. All right, so the last thing that I want to talk about, so we are still going to wrap up a bit early today, but that's all right, is if we just had pure AC actuation. Okay. So I'm just going to make a simple note here. VDC is obviously 0 in this case. Okay. So when only AC voltages are used to bias a MEMS capacitive actuator, the force generated by the actuator is this expression here. So our electrostatic force will be 1/2 times the derivative of our capacitance with respect to position. And then everywhere that I had VDC has gone to 0. So I'm just going to be left with 1/2 V naught squared plus 1/2 V naught squared cosine twice omega t. And expanding this out just a smidge more, I have those two factors of 1/2, so I'm going to call this 1/4 the derivative of capacitance with respect to position times V naught squared plus 1/4 the derivative of capacitance with respect to position of V naught squared cosine twice omega t. So we've got a DC force here, which is setting the mechanical operating point of the system. And then we have a sinusoidally oscillating AC force as well. Now, one thing that is very regularly done, specifically with using AC actuation voltages, is we might choose to electrically excite this system at exactly half of the mechanical resonant frequency, so that our AC force is generated at that mechanical resonant frequency, right? So if omega is equal to omega naught over 2, and then we double that because of the AC term there, we're going to get force generated at the mechanical resonant frequency, which would generally be a good thing because that's where we're going to get the largest amplitude of oscillation with the smallest amount of input energy, okay? So let me just make a note here. To generate a force at the mechanical resonant frequency, of the system, the electrical excitation frequency must be omega is equal to omega naught over 2. And this scheme is used, and I think I mentioned this very briefly in our last class meeting. Sorry, but scheme, there we go, that'll work. In MEMS capacitive gyroscopes. So we haven't really talked about MEMS capacitive gyroscopes at all yet, other than me mentioning them as a thing. So I just want to kind of briefly conceptually talk about why this would be used in a MEMS capacitive gyroscope. Okay. Or why this would be used as opposed to having a DC offset as well would be a better thing to do this, right? So we saw, let me scroll back here really quickly, right? Going back to the very kind of beginning-ish thing here, okay? So the force that we are generating with a capacitive actuator has some DC term and some AC term. If we have some DC biasing voltage applied, then obviously the DC force that's generated by our system is going to be significantly larger. Now, when we're talking about a MEMS capacitive gyroscope, really, we're not going to be experiencing huge amounts of rotational acceleration or anything like that, right? So a gyroscope, for those of you who aren't aware, you probably have several of them in your phone. That's what is used to reorient your screen from vertical to horizontal and all of that kind of stuff when you move your phone around, right? So realistically, the amount of acceleration that you're going to get through everyday use is going to be rather small. It's very easy to lose that signal if you have a large DC bias voltage applied, because you've already caused the device, you've already caused your microstructure to move left or right in a particular direction by some large amount because of that large force. So by eliminating that DC portion, the signal that we're looking for looks comparatively larger than the DC signal that we have to filter out, because there's still going to be a DC term to get rid of so that we can see our signal that we're trying to sense. Yes. For sure. Yes, because it's you have less to filter out. So I don't want to say that DC term is noise per se, because it is not noise, but it is making the signal that we're looking for comparatively smaller. So by eliminating that side of things, it makes it a little easier to filter and then amplify the thing that we're actually interested in. So just for the sake of argument, let's work one last little quick thing here, where let's say that we have a capacitive comb drive. So for a capacitive comb drive with N is equal to 100 finger overlaps, finger height of, what is that guy doing? H is equal to 5 microns, and a gap of D is equal to 2 microns, so the same one that we were working with earlier. I want us to determine the force generated, that's me, the AC force, excuse me, generated by a signal V as a function of time is 5 cosine omega naught over 2 T volts. So this is, like I said a moment ago, fairly straightforward. So our AC force component is just going to be 1/4 times 100, 8.854 times 10 to the minus 12 farads per meter, 5 times 10 to the minus 6 meters, all over 2 times 10 to the minus 6 meters. And then this is going to be multiplied by 5 volt squared cosine, and then twice omega is going to just be omega naught. And this winds up coming out to be essentially just 13.835 cosine omega naught T micronewtons. So just simple application of the formula there. So essentially what we're going to have, just for a quick thing here, what would the DC portion be? You should be able to glean it right off of just this thing. 13.835, exactly right. So when you do just this AC thing, your force is going to range from 0 all the way up to twice, let's just call that F naught, and it's going to oscillate back and forth, where the magnitude of FAC is the middle point, right? So you're going to have no oscillation up to a lot of oscillation, back and forth, back and forth, back and forth. That's another reason why it's a really good thing to use for, excuse me, this is a really good scheme to use for those capacitive gyroscopes and all of that kind of stuff as well. Because as we'll find out when we, 2 to 3 weeks from now, essentially in a MEMS capacitive gyroscope, we have to have a drive occurring. So we have to be generating some sort of AC force causing oscillations in one particular direction in order for us to be able to actually measure rotation, because we're going to be relying essentially on Coriolis force, which is I hesitate to say imaginary force because it absolutely exists, but it's a way for us to measure rotation. And the induced force from that Coriolis force is actually going to be orthogonal to our drive direction. So if we don't have our system oscillating in one direction, it's going to be impossible for us to notice rotation.